In this video, you want to take a look at the sampling theorem and derive the conditions for sampling a continuous time signal and then reconstructing the continuous time signal from the discrete time samples again. Okay, so let's get into the right screen here. And we want to look at this part here. So this is the title. And the goals that we have in this lecture are the derivation of a picket fence signal that we use for sampling a continuous time signal. And then we want to sample band-limited example signal, and then look at the interpolation of a DT signal, look at the sampling theorem as a result of all our investigations, and then also take a look at what that means to have aliasing. All right, the picket fence signal goes something like this. So we have a sequence in the time domain of impulses. So those are continuous time impulses, which are spaced Ts apart. Ts 0, and then it goes also on the negative side, like this, minus Ts, minus 2Ts, minus 3Ts, etc. So that continues to the left and to the right. We're going to call it C of t, equal to the sum n equal to minus infinity to plus infinity of delta of t minus n times Ts. And the areas of those impulses are 1, like this. And what we would like to find out is what is the Fourier transform of the sequence of impulses. So this is a periodic sequence, and so we should be able to represent that in terms of Fourier series coefficients. So we should be able to write C of t is equal to the sum from k equal to minus infinity up to plus infinity of Fourier series coefficient C sub k, and then times e to the minus, e to the plus j 2 pi kt over capital T, like that. So the ck, if we derive that up here, they are going to be equal to 1 over Ts times the integral over an interval of length Ts of delta of t, and then times e to the minus j 2 pi ft dt. But using the shifting property of the delta function, we can see that this behaves like just delta of t times e to the 0, which of course is equal to 1. And so we find that the ck are just 1 over Ts times an integral over an interval of Ts of delta of t dt. And that is just simply equal to 1 over Ts. So now we think of Ts as actually being the interval between samples. And so 1 over Ts would be equal to Fs, which is the sampling rate. So Fs equal to 1 over Ts will be the sampling rate. All right, and so now looking at the Fourier transform, so we want to write Fourier transform of C of t. And that is equal to, because the Fourier transform is a linear transformation, that's equal to the sum over k from minus infinity to plus infinity of ck. Those two do not depend on the time variable. And then we have to take the Fourier transform of e to the j, that should be e to the j 2 pi kt over t. Okay, so now we can think of that as being 1 times 1 times e to the j 2 pi kt over t, and that t should actually be ts. So let's make that into a ts. And remembering the Fourier transform pair, which says that x of t times e to the j 2 pi f0 t in the frequency domain is equal to x of f minus f0. We can say that in this particular case, the Fourier transform of that e to the j 2 pi kt is delta of t minus the delta of f minus the frequency shifting that we have here. So we can write that this is equal to sum over k of ck, and then times delta of f minus, and now we have to figure out what the frequency is. So we can see that we have a 2 pi t in here, and then we have k over ts. So the k over ts is what the frequency is. So it's minus k over ts. And then we can make use of the fact that we know what ck is. That's equal to fs, and 1 over ts is equal to fs. So we can write that this is equal to the sum from k equal to minus infinity up to plus infinity, and the ck does not depend actually on the k. So let's shift this over a little bit. Okay, so we can write here fs times k equal to minus infinity up to plus infinity of delta of f minus k times fs. Okay, so let's take that over to the next slide. And move that over a little bit. Yeah, let's actually do it like this. Even a little bit more. Okay, so we can say now that C of t equal to the sum n equal to minus infinity to plus infinity of delta of t minus n times ts in the time domain that corresponds in the frequency domain to C of f equal to that summation over k. And if we make a picture of that, that's what it looks like. Okay, so we have here the frequency domain. Here we have the time domain. And then we have those picket fence impulses here at Ts, 2Ts, 3Ts, minus Ts, minus 2Ts. They all have an area of 1. And they continue to the left and to the right. And then in the frequency domain, we have another set of impulses, something like this. They are spaced fs apart. So here is fs, our sampling rate, 2fs, then minus fs, minus 2fs, and they have an area of fs. And they also continue all the way to plus and minus infinity. Okay, and let's remind ourselves that fs equal to 1 over ts. That will be the sampling rate. In samples per second. And so now what we are going to do is we're going to take that picket fence and use it to do sampling of the signal that we want to sample. Okay, so let's take a look at how we want to graphically represent that. So we take some function that's convenient in the time domain, maybe something that looks like this. So that's our x of t. And then we make a parallel drawing in the frequency domain of some suitable frequency domain function. Okay, that is going to look something like that. Okay, we do assume that the time domain function is band limited. Okay, so we pretend that this is a Fourier transform pair. This is, of course, not a true Fourier transform pair. A trapezoidal shape like we have here on the right-hand side would translate into some form of a sine x over x, but it's not convenient to draw this here with a real pair of Fourier transforms. Okay, so this is fs, this is minus fs, and we assume that x of t is band limited to some frequency fl. Okay, and fl would be here this one, and here minus fl, and we will, for now at least, assume that fl is less than fs over 2. And we also assume that there is some amplitude associated with that a, so that we can keep track of what's what's going on. So this is what we call x of f. And actually, it should not be repeated here. So let's take that off. That comes later when we do the repetition. Right now, we are actually talking about a continuous time function. And it would not have this band limitation that I have been, it has band limitation, but it would not have the repetition that I have been showing. Okay, so this is our starting point. And now we go ahead and we say that our sampled version xs of t is equal to x of t times c of t, that picket fence function that we just looked at. And that would be equal to the sum from n equal to minus infinity to plus infinity of x of t times delta of t minus n times ts. All right. And this we can in turn write as being equal to the sum of n equal to minus infinity to plus infinity of x of n times ts times delta of t minus n times ts, where we make use again of the shifting property of the delta function. And then we further simplify that somewhat to say that this is n equal to minus infinity to plus infinity of x sub n times delta of t minus n times ts. And x of n in here is are the samples. So x of n is equal to x of n times ts. And this x of s of t is the sampled version of x of t. Now, the next step is to look at the Fourier transform of that. So let's actually try to capture this so that we can see it sort of at the same time. Take it over to the next slide. Okay, so this is the time domain part that we have done now. Now we do the frequency domain part. So x sub s of f is going to be equal to x of f convolved with c of f. Because we multiplied in the time domain, we do a convolution in the frequency domain, and that is going to be equal to fs times the sum from k equal to minus infinity to plus infinity of x of f convolved with delta of f minus k times fs. Like that. And that is equal to fs times the sum over k from minus infinity to plus infinity of x of f minus k times fs. All right, so let's take a look at what this means graphically. So we go back to our two functions. In fact, we can copy those over. So we will take those two functions and modify them slightly. So we had x s of t equal to the sum, and oh, actually let's write that differently. It's better to actually do it in the form of x of t times c of t, so that you can see what we are doing. And then over on this side, we are doing the x of xs of f being equal to x of f convolved with c of f. And then we know what the result is here, so we can write that down. It's the sum n equal to minus infinity to plus infinity of xn times delta of t minus n times ts. And here we can write that this is equal to the sum over the fs, and then the sum over k equal to minus infinity to plus infinity of x of f minus k times fs. Okay, and so now we are going to adjust the pictures here. So the multiplication with the picket fence, that is going to give us impulses here. We just paste ts apart. And the areas of those impulses, they are going to be equal to xn, or x of n times ts. Okay, so they have area x of n times ts equal to xn. And we put it in parentheses to indicate that those are areas of those impulses. And they're spaced ts apart. So here is ts, here is 2ts, 3ts, etc. Here is minus ts, minus 2ts, etc. And in the frequency domain, that now corresponds to, first of all, multiplying by fs. So instead of a, we get a times fs. And then the x of f minus k times fs for the sum over k, that repeats the pattern here, what we erroneously did earlier on, like this, and then like this. And so here is fs, here is minus fs, and it keeps going to the left and to the right. So this is basically how we do the sampling, how we obtain the samples x sub n. And now the next question is, how do we get back from those samples to obtain the time waveform, the x of t waveform that we originally started from? Okay, so what we need to do for that is essentially, let's actually make a copy of this here so that we can write on it. So what we want to do now is we want to build a filter around here. So this is actually not sampling right now, but interpolation, or let's say just filtering. So we want to build a low pass filter here. That captures just one of those repetitions. And of course, we assume still at this point in time that FL is less than Fs over 2. So if we manage to just capture one of those, then in the time domain, we must be getting the original function back. So let's take a look at how we do the filtering. So in the frequency domain, we want to have an h of f that goes between minus Fs over 2 and plus Fs over 2, and we just show that in the form of an ideal filter here. In practice, of course, there is some finite transition between this passband and the stop band. So this is Fs over 2 minus Fs over 2 and 0 here. And then because we had at the top an amplitude of 8 times Fs, we have to actually divide by Fs or multiply by Ts. And so we're going to make this Ts high. And so our h of f is equal to Ts times the rectangular function of Ts times f, or f over Fs. In the time domain, a rectangular function from the frequency domain translates into a sinc function. Okay, so this is going to be h of t. And it's going to look something like this. So here's time. And then in the frequency domain, it is Fs wide and Ts high, so that will make it 1 for the area. So that means that the top here is going to be equal to 1. And then this has to be a Ts. This is a 2Ts, 3Ts, etc. This is minus Ts, minus 2Ts. And so our h of t is equal to the sinc function of Fs times t. Okay, and just to be sure we have the right definitions here. So the sinc of t is equal to the sine pi t over pi t. That's the definition of the sinc function, and direct function of f is such that it's equal to 1 when f is less than 1/2 the magnitude of f, and it is 0 otherwise. And so now what we're going to do is we're going to make or look at x. Let's start from the frequency domain. We're going to look at x of f times h of f. And let's see, that is x sub s of f. Okay, we want to go back from the sampled version to the continuous time version. And that is going to be our x hat of f, what we expect to be, hopefully, x of f again. And then on the time domain side, when this time we multiply in the frequency domain, so we convolve in the time domain. So we're going to get x of t, xs of t, convolved with the sinc, which we just call it h of t. It's going to be a sinc, but we just write it as h of t, convolved with h of t. And that should give us back x hat of t, the original continuous time waveform. Okay, so it's fairly easy to see in the frequency domain, if we go back here, that if FL is less than Fs over 2, that we must be getting back what we originally started from, which was this part here. So we started from this, and that's what we want to get back. And if the Fourier transform indeed lives up to its promise of being unique for each function in the frequency domain, you get the unique function in the time domain, at least within the realm of physically meaningful functions. Then if we pick out just one of those from the repetition of those things, then we must be getting back the original time function. Okay, so let's take a look at that. Okay, so let's copy this over here. Actually, what we have to copy is this one here. So let's take a look what we get from this convolution here. So this is going to be equal to the sum from n equal to minus infinity to plus infinity of xn times delta of t minus n times ts. And then that whole thing convolved is h of t, and that is equal to convolving with the delta function, n going from minus infinity to plus infinity of xn, and then times h of t minus n times ts. And that is equal to, making use of the sinc function, sum n equal to minus infinity to plus infinity of xn times the sinc function of, and remember there was an fs in there, so we had h of t was equal to the sinc function of fs times t. Okay, so we have to multiply here by fs, so we have sinc of fs times t. Minus n times ts, like that. But fs times ts is equal to 1, so we can write that as being equal to the sum n equal to minus infinity to plus infinity of xn times the sinc of fs times t minus n, like that. And so basically, we know that x of s of f times h of f was equal to x of f, just graphically. So therefore, this one must be equal to x of t. Again, from the graphic that we made. And so we can state the sampling theorem. If x of t is band limited to fs over 2, this is called the Nyquist frequency. Then it can be recovered uniquely from its samples xn equal to x of n times ts sampled at rate fs equal to 1 over ts by using x of t equal to the sum from n equal to minus infinity to plus infinity of xn times the sinc of fs times t minus n. To interpolate between the dt samples xn. Okay, so that's the sampling theorem. And then we do want to take a quick look now at what that means if we have aliasing and why that could be a problem if we try to uniquely recover x of t. So if we go back once more to maybe this picture here. And we put that on this slide. So if we sample too far apart, so let's say we're sampling just something like this. Okay, so sampling far apart means that in the frequency domain we come closer together, and so we might actually now have Fs being here, and then we might have something like that, and another one over here, and yet another one here, and so on. So this is minus Fs. So in this case, we have now from the periodic repetition of that spectrum in the frequency domain, so this becomes xs of f, this becomes xs of t. We have xs of f, as you remember, being equal to fs times the sum k equal to minus infinity to plus infinity of x of f minus k times fs. Okay, so that adds up, and we're going to get in the end something that looks like this. And we will in general not know for this part here, the overlapping part, we do not know how to decompose that again. So this is addition, which we cannot undo uniquely. And we have such a band here and so on. So this part is actually called aliasing. Because something from an adjacent part of the spectrum, of that periodic repetition of the spectrum, is spilling over into the current one. And so later, if we take the low-pass filtering of that, so if we go ahead and we look at something like this, in our example, in real-life examples, usually it is more complicated, that spillover between the different parts of the spectra. So this is Fs, this is 0, this is minus Fs. Okay, so if we go ahead now and we do our low-pass filtering for the interpolation, so this would be minus Fs over 2. This is Fs over 2. So we get some extra frequency components in that region where the aliasing occurs. And that yields, if it's an audio signal, that you can easily hear the distortion that introduces. If it's any kind of other signal, it's of course going to be affected just as well. So aliasing cannot be undone by the interpolation process. The interpolation, of course, is the filtering. So it means in order to effectively work with discrete time signals that are obtained by sampling continuous time signals, you need to have the signal band limited. And if necessary, you have to put the filter before you do the sampling so that you do not get the negative effects of the aliasing. So that, I think, completes what we wanted to say here about the sampling theorem and aliasing. It's pretty easy, I think, to see it when you do it graphically with that picket fence. And you certainly have to remember that you have to sample at the rate that's at least twice as much as the highest frequency in your signal.